Hello and welcome back to the alphabet of astronomy. Today is brought to you by the letter Q, and Q is for quasars. Now quasars get their name from the abbreviation QSR, which stands for quasi-stellar radio sources, but quasar is a lot cooler, so I'm happy they've gone with that. The quasi-stellar or quasi-starlike part of the name is because in visible light, these sources appeared as point sources, just like stars. But stars, they are not. So in the mid-20th century, a bunch of radio telescopes were coming online and discovering all these new radio sources. Now, a radio source is just something that's emitting strongly in the radio wavelengths, which is just a longer wavelength of light, ranging from about 1 millimeter to all the way up to about 10,000 kilometers in wavelength. Now, for comparison, the visible spectrum of light is only about 380 to 700 nanometers, so radio wavelength is a huge section of the electromagnetic spectrum that we can't see by eye. So while trying to understand these new radio sources that they were finding, astronomers were trying to match the radio sources to their visible counterparts. And in the 1960s, these two astronomers discovered a radio source that they called exceedingly weird. Now basically this first spectrum contained these really broad emission lines. Now emission lines in a spectrum come from transitions between given energy states that have a very specific energy associated with that, and so that's a very specific wavelength. But these emission lines, they couldn't identify what this transition was that was actually leading to these wavelengths of emission, and they were very broadened. Now, broadening can come from a lot of different effects, but one of them is velocity, and the kind of amount of broadening indicated really, really absurd velocities for these objects. So they had this spectrum that was just really puzzling to astronomers, and they started to find more of them, and so they just gave it a name. So this happens a lot in astronomy, right? We discover something, we don't know what it is, so we just give it a name so we can classify it. And sometimes this leads to some weird phenomena when we later understand it, and it's not at all what we first thought. For example, planetary nebula, which have nothing to do with planets. But in this case, this is where the quasi-stellar radio sources came from, because they were point-like and visible, but in radio, they were these very bright, broad emission line spectra that they just didn't really understand. So one of the first keys to unlocking these unusual spectra was identifying the emission lines. And this was finally done by the Dutch astronomer Martin Schmidt. And he actually identified that they were the Balmer lines of hydrogen. Now, hydrogen is one of the most abundant element in the universe, and the Balmer lines are really well known. But the reason that they hadn't been identified in the spectra is because they were shifted so far from the rest wavelength of the Balmer lines that the astronomers didn't know what they were looking at. Now, there was some debate at the time as to what led to this really large shift of the location of the emission lines. One argument being, that which now we know to be correct, is that they were cosmologically redshifted. And this happens when objects are just very far away due to the expansion of the universe. And so the fact that they were detecting these Balmer lines very far away from where they would be in a rest spectrum meant that these objects were moving away from us very, very quickly due to the expansion of the universe, which meant that they were quite far away. For example, this kind of first quasar, 3C273, had a redshift of 0.158, which at the time was extremely distant from us. Now, translating a redshift into a distance that you might think of conceptually is actually not quite as simple as you might think. There's a lot of different distances in cosmology. There's luminosity distance and angular size distance, and there's just a lot. Co-moving distances and proper distances. So what you even mean by distance is a little confusing. And two, calculating that distance depends on the actual cosmological model that you're using, because you have to kind of integrate along the path between you and this distant object, and what you think happened in the universe is going to depend on the properties that you assign to the cosmology of the universe. So that's why you'll typically see distances given just in redshift, because that kind of avoids all of this confusion. So here's a little plot that shows you kind of how these distances start to change as you get farther away in redshift. Very close by redshifts, the difference in these different kind of distance measurements all converge together, so that things that are really close by to us, there is an actual distance to us that's kind of independent of the cosmological model. But as you get farther and farther away, those effects start to become more important. I'll link below some calculators that you can use to kind of play around with how changing certain parameters of the cosmological model will change with the distances, and how you can compare the different distances between objects. But using this kind of standard lambda CDM, this 0.158 redshift is a luminosity distance of just under 800 megaparsecs. Another early quasar had a redshift of 0.367, which using that same model and luminosity distance is over 2 gigaparsecs, that's billion parsecs. So these are incredibly far distances. And so the fact that we're detecting the light emitted from these objects that are so far away from us means that they must be insanely bright. They have to be really, really luminous to be pumping out enough light for us to see them this far away. So astronomers were kind of starting to build this picture of quasars as these very, very luminous, very, very distant objects that were emitting very strongly, these hydrogen lines, but they still didn't necessarily physically know what they were. They were just observing them and trying to identify the features they were seeing. So what exactly are these crazy quasar things? Well, actually by the mid-1970s, kind of a consensus model was emerging on what quasars were. For one thing, it was becoming generally accepted that they were, in fact, redshifted due to cosmological redshift, that they were far away and very bright. And to be producing this much luminosity, you need a very powerful central engine to be kind of pumping out all of that energy. And so the model for this was kind of mass accreting onto a supermassive black hole, because as that mass falls into the black hole, it's losing all of its potential energy, and that energy is going to basically get radiated away as this very bright luminosity that we see for quasars. Now, if this sounds familiar to you, it's because we've already talked about this, and these are what are known as active galactic nuclei. So I won't get into all of the details again. You can check out the AGN video if you want more. But basically, yeah, these are very powerful central engines powered by the supermassive black hole that are eating just incredible amounts of matter every year. And they also produce these giant jets, and basically how they appear to us is dependent on kind of the orientation. So are we looking, do we see the jet, do we not see the jet, how close are we to the jet, are we seeing through a lot of dust, is it shrouded or not? And so that leads to a lot of variation in quasars and in AGN. So quasars are kind of a subclass of AGN, and in fact the most powerful subclass of AGN. So while a typical AGN, which are very bright and powerful objects, might be consuming about 1 to 10 solar masses of material per year, a quasar can be consuming up to 1,000 solar masses per year. So this is just an insane amount of energy that's just being devoured by these quasars. And in fact, this is the very reason that we see quasars so far away from us. Because remember, the farther away we're looking, the earlier back in the universe we're looking. And so quasars were a lot more common in the early universe, and that's because they just run out of fuel eventually. They can't keep eating this much material because they run out. And so that's why we see a lot of quasars very far away from us, but not so many in our local kind of close neighborhood, because all the supermassive black holes have kind of eaten up all that fuel and they're no longer active. Now, while it was this very strong radio emission that actually led to the first kind of detection of quasars and lent the name to quasars with this radio sources part of it, actually only about 10% of quasars emit very strongly in the radio. And it turns out that that radio emission is coming from the jets of the quasar. So if you can kind of see the jets, then you get a lot of radio emission. Now, if you're looking directly at the jets, then it's something called a blazar, not a quasar. But if you're just seeing parts of the jet, then you're getting this really a lot of radio emission, and so it becomes a radio source. Now, technically, quasars that are not strong radio sources are not quasi-stellar radio sources. They are quasi-stellar objects, or QSOs, rather than QSRs. However, generally speaking, the term quasar is used to refer to both QSOs and QSRs. So when talking about a quasar, we usually specify either radio loud quasar or radio quiet quasar. And in fact, just to add to this kind of terminology confusion, sometimes the abbreviation QSO is used in place of quasar, even though quasar came from the abbreviation QSR. In any case, it's best to be specific if you really want people to understand what exactly type of object you're talking about when it comes to quasars, because there are several different types. But in general, quasars are these very, very active AGNs. They're like the active AGNs. Now, I said that quasars are more common in the early universe, and therefore we see them much farther away from us in general. And this makes them really excellent probes of the early universe because they're so bright, so we can actually see them like really far away. In fact, most of the kind of most distant objects that we've detected are in fact quasars because they're just so bright, they make it easy. Well, easy, relatively speaking. And one thing that's cool about the fact that they're so far away is that they actually make really, really great reference objects because they just don't move relative to our current precision in measuring locations, right? So there's no parallax on a quasar because it's just so far away. And so they actually form a lot of the basis of kind of our celestial reference system that's used by the IAU because they're basically as stationary as you can get in the night sky. Now, we've come a long way since we detected those first couple of very confusing quasars back in the 1960s. We've actually detected hundreds of thousands of quasars now. And those first couple that we talked about with those redshifts of 0.158 and 0.367 that seemed so far away that there was actually a lot of kind of debate about whether they could be that far away are actually not that far away compared to quasars that we know now. As of right now, the furthest quasar ever detected, and this just came out this January, I believe, January 2021, is a quasar called J03131806, and it has a redshift of 7.64, and this is just huge. I know that doesn't sound like a huge number, but it's redshift. Redshift is not really like a totally linear scale. Anyway, it's confusing, but this corresponds to a luminosity distance based on those earlier models that we were using of over 78 billion parsecs. That's so far away. And in fact, the existence of a quasar that early on in the universe is kind of a puzzle to theorists because, it takes time to form a supermassive black hole. And so how did it form so quickly and get so bright that we can see it now? So very cool object. And in fact, the closest quasar we've currently detected is called Markarian 231, and it has a redshift of only 0.04 or so, which means that it's a measly, 200 megaparsecs away or so. So, right next door. Now, quasar, the term quasar might sound like some cool science fiction-y thing, but they're a totally natural part of the universe. Now, granted, they are supermassive black holes that have mass billion times out of the sun that are eating thousands of suns every year and emitting a luminosity that we can see billions of parsecs away. So, they're not like, boring, but they are natural. So I hope you learned a little bit more about quasars today, and thank you so much for watching. I hope you will join us again next time for the letter R. All right, have a good one. Bye!